will turn into a rational equation. You will see, and I'm sure you will recognize it. So in order to find the inverse of this function, the first step will be to replace f of x by y. Agreed? That's the first step. Yes? Everyone? Okay, so this is x plus 20 divided by x minus 5. Karina, did you have other questions? You had a list.
It was just how to put it in the calculator. It just kept messing up.
Okay. But I'll be more than happy to help with that. Okay, that's first step. Step 2, anyone remember step 2 for finding f inverse? Yes, because we are allowed to. We are never allowed to. But in this case, we are, because x becomes the y value of, or the y of f becomes x of f inverse. Okay, and now all you have to do is just put it over 1 and recognize that this is, how is it called? Very important name. We've solved many of them at the beginning of the semester. Specifically, I put it over 1 to trigger your memory. Proportion. This is a proportion. So this is xy minus 5x equals y plus 20. What are we solving for? What are we solving for? I've been carrying your test back and forth so many times. Now I've decided that I have to return them to you. Back and forth, back and forth, back. John. Okay. Good. So we are solving for, one more time. What are we solving for? Of course, y becomes the f inverse. Correct. We have to solve for y. So then I move y and I move 5x. So xy minus y equals 5x plus 20. Okay, so what will be the next step? Okay, so what do we have to do to solve for y? What do you think? Maybe you said it, but I didn't hear it. I'm so sorry. Can anyone give us the next step? So we're solving for y.
Subtract xy.
If I cannot combine, what is the other option and the only option? Thank you. Maybe you did. Forgive me. I'm sorry. I didn't hear. My apologies, please. Accept my apologies. Find it in your heart to forgive me. Thank you. So this is step 3. We solve for y. So then step 4 will be, last one. Yes, replace y by f inverse, the notation f inverse.
When it goes like the x is greater than or equal to?
Correct. Not greater than, but not equal to. Because, of course, the domain of this function requires x not equal 1.
Okay.
There is no other way. Because if x is 1, the function doesn't exist. The same thing here. X does not equal?
Okay.
Correct. Is there anything else? It's a very good question. Thank you so much for asking, because I did not get the chance to show each and every type of function.
Now it says the f of negative 1 of x. And
in other words, it's asking you to show that what we determined is correct.
Okay.
So if this is indeed the f inverse and I determine f inverse comp f or f comp f inverse, what should I get if this is correct? Let me say it again. So f comp this or f inverse comp f. If this is correct, both have to be equal to, indeed, nothing can happen to x. Nothing can happen to x. If these two are inverses of each other, I'm giving you $10 and I take it back. No deal. So if I apply f and then f inverse will cancel the effect of f.
Okay.
So I get x back. If I apply F inverse first and then F, nothing happens to X. Either way. So you want to show one of them?
Okay.
Yes?
Yeah.
Good. Which one?
F,
And then you can show the other. Choose one. We show one.
F comp F.
Good. So you want F comp F inverse.
Yeah.
Or F inverse comp F. Doesn't matter. They are the same. They're both rational functions. It doesn't matter. It really doesn't matter. The method will be the same. So it could have been different if one of them, which is not the case here, is linear and the other one quadratic.
Okay.
One way will be easier. But they're both rational. It doesn't matter. So we wanted F comp F inverse. Good. So this is by definition F of F inverse, right? Because F inverse is the inner function, F is the outer. Are we okay with this so far? Yes? Now, of course, don't cross it out. I'm just explaining what I'm doing. So what do I replace the inside by? 5x plus 20 over x minus 1. Awesome. So I'm going to write it one more time for everyone to see. Good. So now let's look at F. At this point in time, I have to decide what F tells me to do. I have to read or understand what F tells me to do. What does F say? So F says blah plus 20 over blah minus 5. Whatever. So whatever plus 20 over whatever minus 5. Good. So how do I write that? 5x plus 20 over x minus 1. Very good. Awesome. Not to be confused with this. These are completely separate. And the denominator?
Would be 5x plus 20 over x minus 1.
That's it. So one more time. All these quantities have to be identical. If I have here 1500, I have to have 1500 here and 1500 here. If I have here a plus b, I have to have a plus b here and a plus b here. That's what the function is telling us. One more time. F of a plus b equals a plus b over a plus b, 20 and minus 5. Is that clear, everyone? Yes? Agreed? Okay. So now, this is not a very simple situation because this is a complex rational expression. I have to find the least common denominator in the numerator. I have to find the least common denominator in the denominator as we did with rational equations. So what is the least common denominator in the top? Awesome. So then this one needs what? Because it's over 1. It needs an x minus 1. Similarly with the denominator. It's the same thing because it's the same denominator. So can anyone dictate the top? I start here, right? 5x plus 20.
Plus 20x minus 1.
Exactly how we did in 1.6 with rational equations. Identical, everything identical.
We left an x out of the second 20.
Of course. Thank you very much. So then 5x plus 20. And then? So it's negative 5 multiplied by x and negative 5 multiplied by negative 1. Perfect. What will be the next step? So the only difference from 1.6 is that this is not an equation. This is an expression, but the mechanism is the same. So what do we do next? Yes. And also here, the 5x with a negative 5x. What is left at the top? Can it? Yes, but I have to combine them. Exactly. 25x over x minus 1, and I have to flip the fraction from the denominator because I multiply. I have to multiply. It's a division, but now I have to multiply.
And what do I have in the denominator? Very good. Again, what do you expect the answer to be?
X.
Right. If our calculations are correct and we determined F inverse correctly, the answer should be X. Good. Let's see. Is there anything that goes away? X minus 1 indeed. 25 indeed. And the answer must be, as expected, X. So what do we conclude about 5x plus 20 over x minus 1? What can you say about this? It must be the correct inverse of f. Correct. Awesome. Very good example. Very useful because we have not looked at a rational function in class. Thank you. Good. Other questions? Is there anything else you worked on? Is there anything else you would like to go back to? So in the last week, we looked at polynomials, polynomial functions, and we looked at division of polynomials. What I would like to do today, but not if you say, show me another example of this or another example of that. That's always open. That's always on the table. What I would like after that to do today is graph rational functions, which are more sophisticated than what we covered so far, and inequalities that are not the inequalities that we talked about, which are linear and absolute value, but the other two, of course, polynomial and rational. Okay, so is there anything that you would like to go back to? I set up a review with all my 137 classes on Saturday between, I know it's early, but I have a workshop to go to right outside of DC. So 7:30 to 8:30 at Rundle Mills in room 401. I reserved that room. Now, if you want me to come a little bit earlier, if you think we need more time, I will. So there is no traffic. There is no traffic at that time. You are all invited. And if you think you need my help, please come. Okay? So this Saturday, yes. What is it? The 27th? Is it a 27th?
Yeah.
Yes.
Okay.
So you're saying some.
You'll go over in class too, right?
Sure.
Okay.
I will also post that.
Okay.
But some students prefer to be in person, you know, and talk to me about their questions. And so I normally try to have a session before a test anyway, an extra session. So you're all invited if you can. If you want, if you think it's valuable to you, please do. Okay. So we continue then. Do you have any questions? Anything for me? Yes. Mackenzie, go ahead. Any questions? Okay. So let's continue then. Would you like to go back to any polynomial functions? Any questions on that? Division? Yes, please.
When's our actual test?
A week from Thursday.
Okay.
I think it's the 30th,
No, that'd be the first example.
November 1st. Yes. Yes. We only have 2 more weeks, maybe 2.5, maybe 3 roughly till Thanksgiving, and I'm trying to have test 3 if possible before Thanksgiving and not if not after Thanksgiving, because I need 2 weeks to review with you. So that's my target. If we can't have 2 weeks, at least we should have a full week to review. So that's my my thinking. We'll see if we can accomplish that. Okay, so two more sections before test on Thursday next week. So this is a little bit more sophisticated, but if you follow me and if you are patient, you always know that the first example looks difficult and it takes like forever, and then the next one takes 3 minutes, and then the following one takes 2 minutes, and so on and so forth. Okay, so rational functions. Rational functions have way more sophisticated models. They are way more sophisticated models, and they are applied in situations like, and I'll show you a couple of examples after we graph them. They appear in models like, for example, a patient is taking a medication, and the concentration of that specific medication in the patient's bloodstream is calculated with a sophisticated function like rational. Another example that we're going to look at is if we swallow a piece of sugar, the pH level in the mouth changes based on a rational function. So these are way more sophisticated applications than just throwing a ball up in the air and looking at the quadratic function. Way more sophisticated. Okay, more work, and the applications are more difficult. Okay, so what is a rational function? A rational function is a ratio of two polynomials. So ratio, that's why it's called rational. Ratio of two polynomials. I like to divide the group of rational functions that we can look at in this class, because we cannot look at all possible rational functions. We are limited to 3 types. So I call type 1, the first one, type 2, and type 3. No one names them as type 1, 2, and 3, but it's easier for me to explain, and I'm hoping that you will understand easier if I give them a name. So what is type 1? What is type 2? What is type 3? Let me give you an example and we'll discuss. So here's one. Here's type 2. And here's type 3. Now let's see what the difference are among these 3. And I'm going to say from the very beginning that the first 2 are quite simple. Initially, they will look very difficult, or the first example will look maybe difficult, but the first 2 are very simple. The third one, I will not turn it into a mandatory problem. Meaning, if you like it, I'm gonna have a extra credit to choose from, so you will be able to graph this function and get 10 points. If you say no, I'm not interested, then you're gonna choose a different extra credit to solve on the test or final exam. I think that this particular function is a little bit beyond the scope of the course, so that's why I'm not going to make it mandatory. I will show you an example, even more if you need to. But I will show you an example like this one or any other you want to choose. But I'm going to focus only on the top 2 as mandatory for this upcoming test and the final exam. Okay, so now let's look at these 3 and see what is specific to 1, 2, and what is specific to 3. And why I separate these 3 into 3 different types. Something must be going on, right? So let's take a look at the first one. What is the degree of the top? 1. Perfect. What is the degree of the bottom?
1.
So type 1 requires degree 1 over degree 1, or degree 2 over degree 2, or degree 3 over degree 3. What does that mean? Same degree over same degree. That's it. That's type 1. Degree n over degree n. As long as we see a rational function with same degree over same degree, they will all fit the category of type 1. And you'll see in a minute what is different. Okay, let's take a look at the second one. Higher degree in the denominator. Higher degree in the denominator. Okay. That's type 2. As long as the degree in the denominator is higher than degree in the numerator, this is type 2. Okay, let's take a look at type 3. Can anyone tell us what type 3 means? Higher degree in the numerator, but exactly by 1 unit. This is mandatory. higher degree. So it's better to write it as degree n plus 1 and degree n. If the denominator has degree 5, the numerator has to have degree 6. If the denominator has degree 2, the numerator has to have degree 3 for the function to belong to category 3. Now, let me ask you this. When I divide degree n plus 1 by degree n, for example, degree 4 by degree 3, what degree do I get? Right? If I divide degree 2 by degree 1, what degree do I get? Degree 2 by degree 1. If I have degree 10 divided by degree 9, what degree do I get? 1. So what is degree 1? What function is degree 1? Exactly. That's what it will be what it's called a slant asymptote. That line when we divide. So don't worry about it right now. Okay, I started to write something here, but I prefer this notation. Let's start with number 1. So type 1. I'm going to copy this function one more time. So f of x equals 2x plus 4 over x minus 1. Like we did with quadratic and polynomial functions, we are going to have a long list of things that we need to look at before we manage to graph it. Okay, number 1, domain. Number 2, that will be the last one. However, the order of these items is not important. We don't have to go through all these steps in that particular order. And we won't. You'll see in a minute. So I'm just giving you the whole thing. So we can write range, that's fine. However, as I said, normally the range is at the end after we graph it. For this, especially for this function, not for quadratic. Because for quadratic, we know exactly where it's coming from once we have the vertex. But for this function, we can determine the range before we graph it. Okay? So domain range. Very good. X-intercepts. And there, because now we know what? They're what? They're from polynomials. It starts with M, of course. Indeed, it can happen. X-intercepts and their multiplicities. 4. What do you think? Y-intercept, very good. Of course, max-min, if it happens, with a TI-84. Of course, symmetry, if it happens, odd or even. However, I'm interested in 7 and 8, which are totally new. Yes, very good. So we will say that the functions, rational functions, when they are undefined, in general, there is an exception, of course, but in general, when rational functions are undefined, they have what is called a vertical asymptote. They cannot cross that. If it's undefined, the function will never have a value there. So I'm going to write that vertical asymptotes and in the same item, and behavior of the function near the vertical asymptotes. It's a mouthful. I will explain. As I said initially, the first example, it will take like forever. You know that already. So vertical asymptote and behavior of the function near the vertical asymptote. So imagine that, and I'll give examples. So imagine that the function has a vertical asymptote at x equals 2. By behavior of the function near the vertical asymptote, we mean if the function goes to positive infinity, exactly, or negative infinity, or positive infinity, or negative infinity. There are four possibilities. Both sides go to positive. Both sides go to negative. This is the third option, and this is the fourth option. We're going to see that in a minute. So this is what we mean by vertical asymptotes and behavior of the function near the vertical asymptote. Now, there is an exception. A rational function is undefined at the value of x, but it does not have a vertical asymptote there, but a whole. I'm going to give an example of that, and you'll see what happens and when that happens. And last one, last item here, number 8, and that's the only exception. In number 8, we have horizontal asymptote. Finished, James? Thank you very much. See you Thursday. That's okay. That's okay. As long as you finished, I'm happy. Horizontal asymptote. Horizontal asymptote for type 1 and 2 only, or slant asymptote. For which one? For type? Exactly. Only. So let's start with these two pieces of information that we did not have before. Polynomial functions are smooth, continuous functions. They don't have asymptotes of any kind. They're very friendly. This is a much more sophisticated function. It's not that friendly. So let's talk about vertical asymptotes. So let's say I have a function 1 over x minus 3. When is this function undefined? At x equals 3. So x cannot be 3. We can never plug in 3 in this function. Would you agree? Because we cannot plug in x equals 3 in it, at x equals 3, which is not part of the graph, the function will have what it's called a VA, vertical asymptote. When we establish that the function has a vertical asymptote at that point, we know that one of the following four possibilities will occur. Positive infinity to positive infinity, negative infinity to negative infinity, or positive and negative, or negative and positive. I don't know which one. I will know in a minute. I will plug in a number from the left of 3. Close, not 5, negative 5, but close. Let's say 2.9. So if you plug in 2.9 here, just don't calculate anything, just tell me the sign of the denominator. Well, with 2.9 minus 3 cannot be positive. Negative. So then the function on the left-hand side will go to negative infinity. Let's plug in now something close to 3, like 3.1. I only need the sign. Correct. So then I know that the function will, on the right-hand side of the vertical asymptote, will go to positive infinity. These two little numbers, close left and right of 3, gave us the sign. I don't care to plot them. I'm not interested in any of the work. I just use them to the left because I cannot plug in 3. Plug in 3 will be undefined. That's why I have to plug in something close from the left and close from the right, just to determine the sign. So this is the idea of the vertical asymptote. Now let's talk about the horizontal asymptote. Remember from polynomial functions, we had two categories. One which was odd degree, and it depended on the leading coefficient. This was the end behavior for odd degree and positive leading coefficient. This was the end behavior for odd degree and negative leading coefficient, correct? Okay, for even degree, this will be positive to positive for a leading coefficient which is positive and the leading coefficient which is negative. same idea. But these functions do not go to infinities. They approach a number. As x approaches negative infinity, the function gets closer to 5. As x approaches infinity, the function approaches 5 on this other end. This is a horizontal asymptote. So we are going to find horizontal asymptotes for type 1 and type 2. The type 3 will never have a horizontal asymptote, but it will have a slant asymptote, either this way or this way. Okay, so I think we have all the information we need for now to start graphing this. I'm going to copy it one more time. So 2x plus 4 over x minus 1. I will immediately do what? Do all the preparations possible that I may need for now or later. Meaning what? I will factor out the 2 over x minus 1. That's the only thing I can do to the function for now. I will get my table going, the same table we looked at last time with polynomials. And I will ask myself the same questions. What questions? Everything that we just discussed. So let's start slowly. Domain, please. That's not possible. This is not a polynomial function. I wish it were that easy. This function is not a friendly function.
Negative infinity to 1, and then 1 to positive.
Very good. So negative infinity, 0, 1, infinity, nothing. I don't have a number to write under 1. Is that clear, everyone? That we don't have a number for x equals 1? Yes? We all agree? Perfect. So then, because x minus 1, the next example will have that exception. Because x minus 1 is not canceled with an x minus 1 from the top. I don't have an x minus 1 to cancel this with. And this one will stay in the function forever. Then I will write myself a note. X equals 1 must be a vertical asymptote. In the next example, I will show you what I was referring to. Because this is a vertical asymptote, left and right must be infinities. However, I do not know the sign. So what did we do a few minutes ago? We picked the number left and right, close. Not negative 3 and not positive 5. Close meaning 0.9 and 1.1. Just to find the sign. So 0.9 and 1.1. Notice that I do not put them in the table because I'm not going to use them to plot anything. I'm only going to use this to find the signs. So let's plug in 0.9. Obviously the top is positive. There is nothing to discuss here. But what about the denominator with 0.9? Perfect. So what is positive over negative? That's it. Now let's plug in 1.1. Top is still positive. The bottom is very good. So I determined from all my list, let me just show you what we went through and accomplished so far. I have domain. This is done. And I have the vertical asymptotes and behavior near the vertical asymptotes. I know where the vertical asymptote is. Is there only one at x equals 1? And I know what the function does left and right. And I haven't even graphed it yet. Good. Next, I plug in 0 because I have to determine the y-intercept. When x is 0, how much is y? 4 over negative 1, which is awesome. So now from all this list, I have the y-intercept. I want to determine the x-intercepts. How do I determine the x-intercepts? For any function. Right. So I have y equals 0, meaning 2 times x plus 2 over x minus 1 equals 0. When is a fraction 0? Never. When the denominator is 0, the function is undefined. When the numerator is 0. Awesome. Yes. When is this? Or you say, I don't want to remember that. I just want to change it into a proportion, and that's fine too. So this times this equals 0. 2 times x plus 2 equals 0. So from here, I have x equals. That's it. Or you remember that a fraction is 0 only when the top is 0. A fraction is undefined when the bottom is 0. It's up to you. Either one. So I put it in my table, negative 2 comma 0. I'm almost there. This function will have a horizontal asymptote. For all rational functions type 1, the horizontal asymptote is determined by the ratio of the leading coefficient over the leading coefficient. So what is the leading coefficient of the top? 2. What is the leading coefficient of the bottom?
1.
How much is 2 over 1? 2. So I will write 2 is the end behavior, and y equals 2 is the horizontal asymptote. So let's see what we accomplished from the list. We have the x-intercepts, and there is no multiplicity. It's 1. Max min will be with TI. Symmetry, there is no function that is symmetric with a vertical asymptote at 1. So we'll write that down. We determine the horizontal asymptote, and we're done. That's it. So I'm going to write, so my professor knows that I did not forget, f of x definite, f of negative x does not equal negative f of x, and it does not equal f of x. Function not symmetric. That's good enough. I'm more than happy with that. When we graph a function with asymptotes, we must graph what first? What do you think? The answer is the asymptotes. Mandatory, I have to graph the asymptotes first. There are two asymptotes. One that is x equals 1, a vertical line, and the other one is y equals 2, which is a horizontal line. Next, I will plot the points I have. I don't have too many. I have negative 2, 0, and I have 0, negative 4. I'm trying, like before with polynomials, I'm trying to make sense of the information I see here at the bottom. So let's look at this together. From approaching 2, right there, 2, approaching 2, it's coming down and crossing at negative 2, 0. It's crossing the y-axis at 0, negative 4, going towards negative infinity. That's what I see here. From 2, crossing the x-axis at negative 2, 0, crossing the y-axis at 0, negative 4, going towards negative infinity. Done. On the other side, from positive infinity, approaching 2. That's the graph. Okay, so one more time. From approaching 2, crossing at negative 2, 0, crossing at negative 0, negative 4, approaching negative infinity on the left-hand side of the asymptote, and the right-hand side is doing this. So this is f of x, 2x plus 4 over x minus 1. Now I can determine the range. Can anyone give us the range of this function? Careful. Exactly. Exactly. Perfect. So the range is negative infinity to 2 union 2 to infinity. When we talked about functions in chapter 2, I gave an example like this. It's in your book. So we picked a problem that had, there was a rational function at that time. I couldn't tell you what it was. So now I can tell you this is a rational function. It has a vertical asymptote at 1, it has a horizontal asymptote at 2. Let's graph it with a graphing calculator. And I had enough time to prepare, and I didn't. Sorry. When we put in the graphing calculator a rational function, we have to have parentheses around the numerator and parentheses around the denominator. So in y equals, make sure you clear everything else. In parentheses, this was 2x plus 4. Close the parenthesis and divide by x minus 1. There is one other function that I have to put in the calculator because the calculator will not be smart enough to put it itself.
One of the asymptotes,
Not the vertical one,
the horizontal.
because the vertical one is not a function. Very good. Yes, we have to put in the horizontal asymptote. I'm going to choose, although I know the graph, I know it doesn't, I really don't need to see negative 10, 10, and negative 10, 10. I'm going to use the standard just for a second and see, and then I can standard. Zoom 6. Here it's coming, crossing at negative 2, 0, crossing at 0, negative 4, going towards negative infinity. On the other side, and here's the horizontal asymptote. And the vertical asymptote, I have no idea how to put it in this software. Please forgive me. I have no idea. I will ask why the vertical asymptote, the calculator, the computer software does not present that. The more sophisticated calculators you will have to put it in. For old calculators, it's always there. So if I use my TI-86, so we had 2x plus 4 divided by x minus 2. No, it was x minus 1. And then 2. And I graph with zoom standard. I think it will present the vertical asymptote. Yes. See? But this is an old calculator. You see the vertical asymptote, you see the horizontal asymptote, and the rest of the function, of course. Right? Yes? Okay. So I don't know why the new ones, you have to put them by hand. Any questions on this? The only difference between type 1 and type 2 is the horizontal asymptote for type 2 is 0. Why is it 0? Because the denominator is so much bigger than the numerator, at infinity will be 0. That's the only difference. So type 2 is even easier, I would say. Okay, let's look at type 2. It was function f of x equals x squared plus 3x plus 2 divided by x minus 1. And then I will show one with a hole in the graph. Say it again. I couldn't hear.
That one was type 3. You had that one for type 3.
Oh, the type 3. Yes, of course. Of course. I copied the type 3 instead of type 2. What was type 2? What did we choose for type? Yes. Yes, thank you. Sorry. So this is type 3. So we look at f of x equals x divided by x squared minus 4. Thank you. Good. So the numerator is degree 1. The denominator is degree 2. The only difference you will see is just the horizontal asymptote. Everything else is identical. Okay? So now let's take a look at what will I do first? Yes, I have to factor a denominator. How? Very good. Very useful because now I'm able to determine what? The domain and x, not x-intercepts for denominator, but the domain. Good. The x-intercepts are only from the numerator. Good. So can anyone give us a domain of this function? Negative 2 has to be excluded, if that's what you meant, yes?
Negative 3 and negative 2, negative 2, 2, 3, 3.
Exactly. So we cannot have plus or minus 2. Perfect. Good. So does this factor simplify with a factor of x plus 2 from the top? There is no factor of x plus 2 at the top. Does this factor simplify with a factor of x minus 2 from the top? No. So these two stay in the function forever, which means that x equals negative 2 is,
Very top.
and x equals 2 is, that's it. What did we say about the horizontal asymptote for type 2?
Zero.
Always 0. Here's one more time why. When x approaches a huge number, even if it's negative or positive, this expression will be so big in comparison to the top one. Like imagine, let's say we have a cake and we want to share it with everyone coast to coast. How much will everyone get? Right. So that's the reason why y equals 0 is the horizontal asymptote always, forever, for type 2. Any function, rational function type 2, the horizontal asymptote will always be 0. Why? Because this is so tiny and this is so big at infinities. Let's plug in 0 and see what we get. Exactly. 0 over negative 4 is 0. Perfect. Since you said vertical asymptotes, I know something happens left and right. What do I write left and right? Once I write VA, what do I write left and right? Infinity, 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 infinity. It's a must. Once I say vertical asymptote, I know that that must happen left and right. It's a law. So when I say a vertical asymptote, let's come back here. When I say this is a vertical asymptote, left and right has to be this, or this, or this, or this. Mandatory. Good. I don't know which one. So with negative 2.1, negative 1.9, 1.9, and 2.1, I will verify. With negative 2.1, the sign of the top. With negative 2.1, the sign of the top. Very good, awesome. The sign of this factor.
Still negative.
Very good. The sign of this factor.
Still negative.
Good. 3 negatives.
Still negative.
Awesome. Very good. With negative 1.9, the top. Perfect. The x plus 2. Tom, finished? Thank you very much. See you Thursday.
That's positive.
So now the bottom is positive. What about this? Negative. Negative over negative. Awesome. That side is done. Right here, 1.9. The sign of the top with 1.9. The sign of x plus 2 with 1.9.
Positive.
And the sign of x minus 2 with 1.9. Good. So what is the sign of this infinity? Awesome. Last one with 2.1. The sign of the top. The sign of x plus 2. And the sign of x minus 2. So the sign of this is excellent. There is nothing else because I already have 0, 0. So when the fraction is 0, when the top is 0, I already have it. So that's the x and y intercept. It's done. The only thing is that in this case, this function is symmetric. So when I plug in negative x in it, negative x divided by negative x squared, which will be x squared minus 4, and this will be the opposite, which is negative f of x. When this happens, f of negative x equals negative f of x, what type of function is this? It's not with respect to the y-axis, but odd function. Good. So I want to make sense of the information I have before I attempt the graph. Here's what I see. From approaching 0, it drops to negative infinity on the left-hand side of the first asymptote. from 0 to negative infinity. Let's see in the middle. From positive infinity, crosses at 0, and goes to negative infinity. From positive infinity, crosses at 0, and going to negative infinity. On the other side, from positive infinity, approaching 0. One more time, from 0 to negative infinity. And then in the middle, from positive infinity, crossing at the origin, going to negative infinity. On the other side of the asymptote, from positive infinity to 0. That's the graph. So when we graph functions with asymptotes, what do we have to graph first? Now, I am not praising a method versus the other. I just wanted to show that I think that if you understand my table, you will not have to go through all these steps. No, I just am ahead, sorry. I think that going through all these steps will be difficult. So, step 1, determine symmetry. Step 2, find the x-intercept, the y-intercept, find the vertical asymptote. By the time you're done and the information is not summarized, how do they come up with this? They just plot 1,000,000 points. But that takes half an hour. Again, I accept the method. It's a very legitimate method. It's good. But how, if I don't summarize the information, I will not know what to plot, where the asymptotes are. So use the method you like. But I recommend, if you understand this table, you will have, I think, no difficulties in graphing the function. So I have to graph, this will be an overkill. Why? Because this is y equals 0. There is no reason why I would plot again the horizontal asymptote, graph again the horizontal asymptote. Okay, but I do have to plot, or graph I should say, x equals negative 2 and x equals 2. And now I'm ready to graph the function. Let's do that. Again, from 0 to negative infinity. Is this portion clear? Here it is. In the middle, it crosses at the origin, so it's coming from positive infinity going towards negative infinity. From positive infinity crossing at 0, 0, going towards negative infinity on the left-hand side of this asymptote. And on the right-hand side is this. Is this function symmetric with respect to the origin? It better be, because we showed it was. Any questions? So this is the function f of x equals x divided by x squared minus 4. Any questions here?